Καλημέρα συνάδελφοι. Καλωσορίζουμε τον Ανδρέα Πολύδωρο στη σχολή, ο οποίος έχει υπηρετήσει στην Ακαδημία για πάνω από 45 χρόνια, στο University of Southern California και στο ΕΚΠΑ, στο τμήμα φυσικής. Παράλληλα, ίδρυσε την εταιρεία TrellisWare Technologies στο San Diego, στη Καλιφόρνια, το 2000, όπου εργάζεται πλέον μετά την εξυπηρέτηση από το 2022 ως ερευνητής, ως στέλεχος εταιρείας. Ο Ανδρέας μας δώσει μια ομιλία σήμερα στα ερευνητικά του ενδιαφέροντα με τίτλο Distributed Beamforming, Research Advances and Research Challenges. Θα ήθελα απλά να πω το εξής. Τον Ανδρέα είχα ακούσει από το 1997, όταν πήγα για μεταπτυχιακό στον Μπάφαλο, από τον Άντλι Φάμ, τον καθηγητή, και τον γνώρισα κάποια χρόνια αργότερα σε κάποιο συνέδριο. Θεωρώ ότι είναι από τα μεγαλύτερα ονόματα στο φυσικό επίπεδο τηλεπικοινωνιών του παρελθόντος και του παρόντος, και με χαρά να ακούσουμε την ομιλία του. Η ομιλία θα στα αγγλικά, οπότε the floor is yours.
Πρώτα να ευχαριστήσω στα ελληνικά. Ευχαριστώ κύριε Κοσμήτωρα. Τιμή μου είναι να είμαι με φίλους και να μου επιτρέψετε να πω μερικές ερευνητικές σκέψεις σε ένα θέμα που με ενδιαφέρει. Είμαι και μισός κριτικός για αυτούς που δεν το ξέρουν από τη μεριά της μητέρας μου. Έχω και σπίτι σαν ταυρολίτη πια, οπότε δεν μπορείτε να απαλλαγείτε από μένα εύκολα. Τη μόνη ψηλοδιόρθωση πριν αρχίσω την ομιλία που θα κάνω είναι δεν είμαι ο ιδρυτής, είμαι ο συνιδρυτής. Αυτό έχει σημασία, για να μην νομίζουν οι άνθρωποι ότι περπατάω πάνω στα λεφτά. Περπατάω πάνω σε κάποια λεφτά, αλλά όχι σε όλα τα λεφτά. Οι συνιδρυτές είναι σημαντικοί. Κύριος Πυρόπουλος.
Ναι,
μπορεί να έχουμε βρεθεί και στο Eurocom, δεν θυμάμαι.
Ναι. Στο Αρβανιτάκι.
Στο Αρβανιτάκι, τέλεια. Gentlemen, since there are no ladies, I'm going to switch to English. It's a little bit easier for me. However, I'll entertain any question anytime you want in any of the two languages that I think I can understand. The topic is distributed beamforming, recent advances and recent challenges. I added the challenges for those who are interested in some potential cooperation down the road for research. I wear my glasses here for a second. I'll briefly discuss the system aspects of distributed beamforming. I'll discuss a particular important component called phase calibration. The fine print means subtle but important details. And then research challenges. I also added references. I also added 3 appendices which I'm not going to cover. For those interested, you can go through them. The presentation will be available to everybody, and I will be reachable to everybody for any aspect that you'd like to discuss. It would be my honor and pleasure to do so. The problem statement is kind of easy, and I think the coloring tells us. You got a bunch of radios. The radios are distributed in space. They're not connected by wires. They're wireless radios. And what they want to do is send power to a destination. And what they want to do actually is do it in a way where their phasors align. Because if the phasors align, if you don't align the phasors, the average power of n waveforms is n. The gain is n on average with random phases. But if you align them, the voltage is n, therefore the power is n squared. So for large n, you get a very significant gain if you can manage to do that. Where do you need it? There's a bunch of applications. You want to reach further in ad hoc networks, Internet of Things networks, and so on. So ad hoc networks, you might want to reach a fixed range, but lower the power that you're using, so your battery lasts longer. You might want to transmit high rates, as you know, as per Shannon, the SNR in the log gives you high rates. And furthermore, there's no single point of failure. If any one of these transmitting radios breaks down, okay, you got n-1 radios. For large n, the losses are small. So there's a bunch of advantages to this. And so the first question I would like to answer is, we know about collocated arrays. You get a bunch of antennas spaced lambda over 2 apart. It's a classical array. So how is that different? And why bother with that if you could collocate the radios? And the second question is, okay, so how do you do that really? This is a nice problem academic statement, but doing it is a different story. This is an interesting research topic. I think the first papers appeared in the early 2000s. Then the first decade saw a lot of activity. Any of the references, you'll see that. Glorious names, Vince Poor and other people got involved. So for the first 10 years, there was a lot of papers and citations. It continued in the 10s, more with experimentation. Different people started experimenting and demonstrating in various versions, and then it started tapering off. So right now you won't see many because academically, let's just say, people think that the topic has been exhausted. It's not so, as I'll point out. But this is kind of the publication curve, if you wish. This is a versed audience. I'm not going to spend any time explaining to you what phase coherence is. The talk was also given internally into our company, and many people in electronics and software and hardware don't know systems aspects. So I may be forgiven for explaining to them what two coherent sinusoids are. The one thing I'll point out is that you can only define coherence for the same frequency. To us, this is automatic, but not to everybody. That has a negative implication because many systems up and down use different frequencies, not only cellular and Wi-Fi, but even satellites. The reason I'm saying that is I was aspiring originally to reach satellites because you can and provide high data rates. But if the up frequency is 14 gigahertz and the down frequency is 27 gigahertz, you can't do it. So it's a kind of you got to be careful. This is a system that works in a TDD fashion where the same carrier frequency is used up and down. I'm not going to deal with oscillators much. The point is the following. What makes the problem challenging and interesting is that each radio has its own oscillator. When you buy a chip from Altera, whatever, it's an integrated chip. Everything is in there packed, including the oscillator. Contrary to the early literature in the early 2000s, where people thought that they could, reach the VCO like a classical PLL and so on and so forth and change the phases, you can't do that anymore in integrated circuits. So you get a bunch of oscillators distributed. You can synchronize. You can assume that their clock rate or crystal rate is kind of steady. But even the slightest drift in frequency will hurt you. But most importantly, the phase of each oscillator is independent, and you cannot analog affect it. You can, however, affect it in the baseband, in the digital domain, and that's what people do. Whatever correction you want to do, you do that baseband, and then you upload or whatever, upshift the frequencies and go. So you'll see digital techniques applied here, and they work. But the fundamental point, which is very different, for instance, from collocated arrays, is that the oscillators are independent. In a collocated array, you have one oscillator, baseband oscillator, that feeds all the elements. Okay, so things are quite easy there. So it's like the way I represent it to people, and they like it, is it's a bunch of wild horses running around, and you're trying to herd them, cats or horses. It's an interesting thing to do.
Yeah. Do you assume that the oscillators are synchronized in terms of frequency offsets?
They do what?
Do you assume?
Yeah, please.
Do you assume that the oscillators are synchronized in terms of frequency offsets?
No, you estimate the frequency offset.
Okay, so
you calibrate.
You do not assume that, right?
Well, they're within, some small ppm. Okay.
Right.
But no.
Okay.
The whole theory resides on actually correcting.
Okay, great. Thanks.
Not only you estimate friction, this is critical, by the way, it's an interesting point. You must absolutely, as I'll speak later on, I'll show later on, you got to come within like 10 hertz, for reasons that I will explain, which is interesting to estimate within 10 hertz, you can. And that's pretty much all you can do. So no, the theory does not assume perfect frequency sync. It assumes within correcting capability or within what the maximum likelihood estimator can give you. And you apply maximum likelihood in practice and it works. Okay.
Okay. And another question, the distributed oscillators transmit the same, do they transmit the same signal, different information? What is the, or you are going to talk about that later?
Okay, yeah. So what they transmit, you mean?
Yeah.
Yeah. The problem statement, thank you, which I didn't explain, is the following. The first version thereof is the same signal. So there is a source, as you'll see somewhere, and the source disseminates the message. Let's say there's a previous hop, the source says something, broadcasts, everybody hears it, decodes it, so everybody possesses the same message. And now they want to beamform that message to the source. As I'll explain later on, you can think of it this way: if I have plenty of SNR and the destination is nearby, I can use the extra SNR to transmit different messages, to multiplex them. But even better, if the receiver has an array of itself, then you can use the degrees of freedom to do MIMO, to do actual distributed MIMO and increase the sum rate. But for the first version, as per the problem statement, let's assume they all have the same message. Clear? This is just what I just said before. In the past, when I was teaching synchronization at USC, we had phase lock loops and everything else, and you know how you create a narrow signal and drive the VCS. This is all gone now. You have a local oscillator in the lower picture. There's no input to the local oscillator. It's running independently. Everything happens at the DSP level. Okay, so that's basically the new world. This is purely academic. I'll skip it probably, you know it all because you teach it. I will mention the following. You have a transmitter that has an IQ, phase and quadrature mixer. Sum them up, the signal goes out. On the other side, you have, on the receiver side, you also have an IQ mixer, and you take the two messages out, the in-phase and quadrature messages. You got to be careful with the signs. I will not mention popular textbooks right now, but they have the signs wrong. So you have to be very careful with how you assign the signs. But this is known theory. All it says is that you can use complex calculus in phase and quadrature baseband representation to transmit and receive. And the key thing that I want people to remember from this, which again, by the way, I teach that in the graduate level at USC, that my charts are in the, you need some proof for all this, and compact proof, and I think I'm offering a compact proof of baseband representation in case feel free to use it anytime you want. I think people find it interesting. So the bottom line is this: if we work on baseband, you have a baseband complex signal M, IQ. When you transmit at baseband, you multiply it with a phasor that has a phase of the transmitter, e to the j theta transmitter. Then the channel itself adds a rotation, e to the j theta channel. You add noise, you receive it, and then at the receiver, you multiply it with a complex phasor, e to the minus j theta r. The bottom line is very simple. Phase-wise, when you transmit, you add a phase at the transmitter, and when you receive, you subtract the phase at the receiver. That's the thing to take away. If you think of phasors, it's e to the j theta and e to the minus j theta. If you think of phases, it's adding a phase at the transmitter and subtracting a phase at the receiver. This is known, but I'm using it as a refresher because I will need it. Somebody might say, what is this e to the j theta channel? Let me explain right away. Right now, I'm assuming a line of sight channel where only a phase rotation takes place. I'll discuss multipath and other aspects later, okay? But this is just a very simple model just to get going.
And the signal attenuation is absorbed in M?
Yeah, I mean, there's an SNR. Think of the gains being one. Everything gets absorbed in the SNR, okay? The collocated arrays, sure you're teaching it here. It's a bunch of antennas connected to a base, to a processor. And in collocated arrays, because they're half a wavelength apart in space, you can adjust the delays and steer a beam. You can see the line going in some particular direction versus the bore side. It's important to remember, in other words, that in classical phased arrays, you can define a direction. I want to beam there. Okay. In distributed systems, there is no sense of direction. You don't beamform to a direction. You actually, as you'll see, beam spot to a point. That's one difference. Conversely, in collocated arrays, by symmetry, I can have receive beamforming. In other words, instead of transmitting that way, I can receive from that way. Okay? To dissolve a popular misconception, in distributed systems, there is no distributed receive beamforming because each radio is independent. Okay? What people do is then they transmit to a location at the receiver side. That's different. Okay? So there is no such thing as receive beamforming in a distributed sense. Here you'll see the differences in array patterns. Okay? So for a collocated, this is let's say 10 collocated antennas, lumped with 2, and this is the 360 gain pattern. You can tell, and I think we arranged the beam to be at 0 degrees. So you get power, at 0 and 180. It's a vertical array, and very little power around it. Okay, so most of the power is in the beam. When you have a distributed set, and you can see the red dots here, the red dots are the radius. Some radius here, I think the radius is 100 meters. You got 10 radius in a 100 meter location randomly placed, and you can see now, I call this pattern myself an urchin, a chinos. You've got the beam, all right, over there, same game as here, but you cannot really regulate. You don't get a nice clean thing here. You get power all over the place. That's kind of important to remember from interference and other purposes.
So just a question.
Yes, please.
I'm just trying to get the plot. So the reds are the transmitters?
The red are the transmitters, yes.
And the power is distributed?
The power is meant to go here. Sorry. The power is meant to go to the receiver here. This is the receiver. This is the receiver here for collocated, and this is the receiver here for distributed. And in both cases, you get the same gain at where you want it to go. So the gain here is the same as the gain here.
So, sorry, I missed where is the receiver?
The receiver is here at 0.
I see.
Just like here.
I see.
But in collocated, you basically direct the energy here, and very little goes around.
I see. Okay.
It's a beam. It's a real beam. There is no beam in distributed beamforming. There's no beam in the same sense as this. But this spot here gets the energy fully. But you can't really, I'll discuss a little bit the side thing, but you can't really regulate the pattern you're going to create in 360. It's kind of random, okay? And sometimes it will be small, sometimes it will be large. On average here, if you have n radius, this will get n squared, and the rest will get n. It's like, beaming randomly around. Think of everything other than the destination as just being a random phase going around. So on average is n.
I see. Thank you.
Is that clear?
Yeah.
I'm going to say here that actually there is a width here, and it has been measured, and it's in meters. So if you beamform 3 kilometers away, you get the full power at 3 kilometers, exactly as expected. And if you move another radio and measure the power, a few meters this way and a few meters this way, you get full power. And then it drops to n. So there is a little width, okay, that's very small. But that's interesting because if you have antennas nearby, within a few meters, they will get the full energy. So there's a patch, there's a little patch of energy being highlighted, But nothing compared to the collocated. Clear? Well, this is from a paper we wrote, and it's referenced here, back in 21. My collaborators, Ioannis Zagres, who is now an assistant professor in Padua, and Aris Mustakas, who is a very well-known physicist at the physics department, they contributed greatly. Aris did too. Basically, if you receive some waves here with some proper weight plus noise, you assume that each transmitter can change the phase properly through the beamforming operation, and the result is that you get a power at the receiver, which is this. But notice that the power is a function of time. You might say, why time? Well, because first of all, the phase doesn't stay fixed. It starts at nice beamform power n squared, but phase noise and frequency offset drift change, and you'll see the curve in a second. So you can't last forever. It's very critical to find out how long you can stay fixed power-wise or adequate, because then you need to recalibrate and restart. So this points out to the fact that you're going to have a frame structure. You calibrate, beamform, send the data, recalibrate, beamform, send the data. So you have a frame structure. The question is, how long does it last? I'll discuss it in a second. So phase noise and frequency drift, more importantly the frequency drift, the question you asked, even for a small frequency offset, let's say 10 hertz, in 10 milliseconds, you'll have shifted 36 degrees. It starts to hurt. So frequency offset, not compensated, hits you. The theory also included Doppler spread. You assume that the gains might change by Doppler spread, and with some particular statistics, which I described the parameters here. And you can write a nice theory. It turns out that it lends itself to nice analysis. So the bottom line is this. If you look at the paper and you look at the analysis, it tells you basically that you start at full gain at time 0. This is for various, number of transmitters and so on, and frequency drift parameters. You see that, eventually, after time passes, you hit this thick line, which is the incoherent gain. So you write down the incoherent gain, you start coherent, and it drifts down to incoherence. Okay, and this is for 3 transmitters. This is for 10 transmitters. So it is pretty critical to analyze this and decide how long can I stay with adequate gain. We usually define the adequate gain so that you're, just some portion of the full gain. Like you lose 2 dB or something like that. And after you do some careful analysis, you realize that for most practical systems in L-band, in other words, transmissions at the gigahertz plus, you need to refresh every 10 to 20 milliseconds. So if your slot size is 1 millisecond and you refresh every 10, okay, you take a 10% hit in throughput. If you refresh every 20 milliseconds, you take a 5%. You expect some hit in throughput through this recalibration process, but hopefully the gains you get overcompensate for that.
Andrea, 0 seconds, you assume you assume that they are synchronized, and then you lose this synchronization.
Yeah, so here you're perfectly synchronized. Here you're perfectly synchronized, phase and frequency. And then basically the frequency offset starts rotating. Okay? Remember, each one of them will estimate separately. Okay? So they have a random variable offset. Okay? So they start synchronized, but then actually at time 0, there is a frequency offset, but at time 0 it doesn't matter. Then it starts rotating slowly. But it rotates independently per radio. Okay? And therefore you start seeing drift, non-coherence, basically. That's what's happening. The key point here is that to get a Doppler spread effect, you have to have large dynamics. So, multiple of that. So it's not the Doppler spread that matters much, but the frequency offset is very critical. And we did measurements with software-defined radios and so on, and the phase noise aspect is not significant either. Originally, because there's phase noise in the oscillators, we thought it would be significant. It's not. Not in the bands we're looking at, but the frequency offset is a killer. Okay. That simplifies things because you can compute, as you see later on, you can compute what frequency offset you expect mathematically. And the other amazing thing I can say is you work in a real world, you realize that the theory is smack on. The bounds are smack on, the analysis, you do measurements, and they are exactly what the theory predicts. It's pretty amazing. Theory is good. It works. I'll discuss frequency offset in a second. Any more questions on this? So I'm basically saying expect a cut in throughput 5 to 10% for daily calibration aspect. Okay. Now that we understood that it's a game of phases, adding and subtracting phases, let's understand the basics like as a little homework, okay? You got a destination up there, and you got 2 nodes. O means ordinary, and R means reference. You'll see why reference later on. But let's say you have 2 nodes in a cluster, O and R, and they both want to send a coherent signal to D for destination. Okay. And the lines, as you can tell, have different phases attached. The destination has its own phase, theta sub D. In other words, the oscillator at time 0 has a phase, theta sub D. The ordinary node has theta O, so the notation is pretty straightforward. You know? So everybody has their own phase, okay? And there's also the phase of the links. Each link has its own phase. And because the distances are random and different, each link has its own random but fixed value. All right. If the two transmitters O and R just send signal randomly, and this is indicated as phase from 0 to D, and from O to D, and phase from R to D, you write down these some subtractions as I pointed out, and you get that. It's visible that if you don't do anything, you're not going to get coherence randomly. Okay. Incidentally, let me stop here for a second. As things rotate, if there is frequency offset later on, they will on occasion align. This is what Bletzas did about 20 years ago. He called it random or opportunistic beamforming. And yes, indeed, when phases change randomly, eventually they align. The problem with that is that it happens rarely, so you can't expect much throughput. So we want high throughput here, we want consistency. Okay, so how do you correct this situation? And what people thought since time immemorial is what it's called closed loop. So here's what happens in closed loop. O sends a signal, a probe, a known sequence to D. Step 1. D estimates the phase difference with respect to itself. So it estimates whatever comes in minus its own phase, and it sends back a message. You know, the wingled red line is a message. It tells, with a digital message, hey, you're, 72 degrees off, changing. Fine. If O decodes the message correctly, it switches its phase. It will arrive coherently to the line of D. And it also does the same with R. R then sends its own probe, D measures it, sends a message back to D, and it tells what it is. So you can tell that by a handshaking procedure and change of messages, you can align the phases. So I'm the destination, each one of you sends me a probe, I read it and say, hey, you will change your phase by so much. You change your phase, okay, eventually, after with all that, you will align phase-wise to me. This is called the closed loop solution. But there's a catch with it. It involves a message, meaning the destination and the nodes must be at a distance where they can decode the message, meaning a positive SNR for the decoding process. That limits the range right away. I need to tell you something, you need to hear it. So D cannot be too far from the nodes. That's the catch on this. But this is what most people did. They did a lot of variations. Instead of giving it a message, they called it one-bit feedback. In other words, they sent back a closed-loop process that lasts forever and so on and so forth. You can devise all kinds of, homeworkish aspects to it, but in practice and in a dynamic environment and with many nodes, you can tell it's not very interesting. But that's what people wrote a lot of papers on for a long time. Here's an alternative. An alternative is to have D broadcast a probe, just like all transmitters can send a probe, base station sends a probe. Everybody can send a probe, a known signal, in other words, a beacon or whatever. And we'll use the principle of phase conjugation. The principle of phase conjugation relies on channel reciprocity, and channel reciprocity basically says that in the frequencies we're interested in, if somebody transmits here and there's a phase, if I transmit to them quickly, let's just say, it will be the same phase. So if the distance doesn't change between the two nodes, whatever phase comes this way is the phase that goes that way. It's called channel reciprocity. That's important. That's an important principle, and later on I'll discuss the physics behind it and how physicists use channel reciprocity or system reciprocity. Because we can use what we call conjugation. So what we're going to do is D issues a probe. That probe is heard at O and R. These guys measure a phase. They conjugate it, meaning they send the negative back. And let's see what happens then. Well, if you do the math, and assuming that as per symmetry, the phase of O to D is the same as the phase D to O, I just explained it, so this difference is 0, you'll end up observing that you still haven't solved the problem, because the phase arriving after the conjugation at D is actually dependent on, is this term here, and it depends on the phase of O. So if R sends it, it will be dependent on the phase of R. This is common, this is the phase of destination, but this is the phase of the O, and if it's another O, it's another phase. I haven't solved the problem yet of incoherence. But now, if you observe that, you're saying, and you really think and think and think and think, that's what I was telling you before, it just dawned on me that what I need to do is add the term that cancels the dependence on O. Okay, this is about mirrors, just to entertain you on mirrors for a second. A regular mirror reflects the light. A regular mirror reflects the light in a way that this direction gets negated, but the vertical direction stays the same. A conjugating mirror reverses both directions in this way, and vertical and horizontal. And there's physics and experimentation to build conjugating mirrors. We can discuss that separately. So I'm not using mirrors here, I'm not using the principle. But it's a deep theory, actually. People are using it for a lot of applications, ultrasound and so on. It's an interesting principle. Here's the key realization. Hey, if I could add a constant to each node, say node O, which constant is some term to be determined, some fixed term, minus twice the phase of that, hey, I get rid of the dependence, because if I add this term here, I'll end up with this quantity, which is an independent term, minus twice the phase of destination, but the destination phase is common to all, it's just a destination phase, and the B, the parameter, I just defined it such that it doesn't depend on the node. I achieved coherence. That was the bright idea. Find a way to add a term that cancels the node-dependent double phase. So how do you define B? The next question is, how do you define B? It looks easy on paper, but how do you define B? Okay, and here's the other invention. I'll define B, we'll define B. We can discuss the details later on the research items. People have not really compared closed loop with open loop solutions like this in earnest. You know, we did open loop, but it's interesting to find out what the systemically means in terms of the two being competitive. here's how you get B. You introduce a reference node. One of the nodes in the cluster, the beamforming cluster, we will call it the reference node. Okay? And in fact, we will do some local calibration such that B will be twice the face of the reference node. And since the reference node is known to all, you'll end up with, at the end, twice the reference face minus twice the destination face, independent of the nodes, and they all cohere. Okay? So let's use the reference node. How do we get that to work? Two ways of going about it. Again, you replicate the closed solution one. You replicate the closed loop principle. You basically, everybody sends a node to the reference node, the node reads it and tells you back what it is, sends you a message, in other words. So you can kind of replicate the closed loop solution, but locally. But again, it has the same limitation. You need an SNR. And the other invention, it's my invention, is use conjugation, phase conjugation, also locally. So, George is the reference node, and I'm one of the members of the cluster. I send a probe, he conjugates, sends back to me. Okay. That way, I computed twice, just per my principle, I computed twice the phase difference between myself and the reference node. Everybody does the same with the reference node. They all computed twice the phase difference between themselves and the reference node, and that's the correction term that they add. So, stage one, we all ping pong with a local reference and the conjugation principle, and we compute this correction factor, we store it, we've done it quickly, it's local, can be done, some range, no message involved. We computed our correction term, then stage two, the destination issues a probe, we do the conjugation, add the correction term, we beamform, and it works.
Basically, you avoid the messaging between nodes that are far apart from each other, and you base your estimation on the phase that is transmitted. So you must have
you must have a reliable channel with respect to the phase. Phase is more...
Phase is easy. Phase is easy.
But
I'll discuss the grammar of it. Phase is easy.
You may have noise there. And,
I'll discuss that.
But definitely, this is better than decoding. This is what you're doing.
Yeah. You'll see for sure. Absolutely.
So you message phases.
You don't message phase, you facilitate the estimation of phase. But look at it this way,
okay.
to understand why it's different. When you have a signal, when you decode a signal, right, you send me back, and I want to decode it. The symbol SNR must be positive in dB, right? Even with turbo code, it's got to become the dB. But if you send me a training sequence with 100 symbols, 20 dB, the cumulative SNR is the SNR per symbol plus 20 dB. So even if our SNR per symbol is minus 5 dB, by integrating coherently over 100 symbols, I end up with 15 dB parameter estimation SNR, which is plenty to get you the phase down to a degree. The trick is, in other words, estimating a parameter, a fixed parameter, over a number of samples, shifts the SNR to the negative territory. Is that clear? I'm basically exploiting the difference between decoding and estimating. Just point out there's some people in Michigan State that are trying to replicate the true collocated solution. They assume they know exactly the distance. They use some very fine probing mechanism to basically estimate exactly the distance, therefore the phase. It's not a practical solution for all practices. Maybe within a room in 60 gigahertz you can do that, but it's not something for the open field. So I'm not going to spend time on that. The fine print is, very quickly, I assume that the up phase, uploading and uplifting or whatever, conversion and down conversion chains are the same. In practice they're not, okay, because the chains have different filters and so on. So you're really careful, you'll see that the up phase of each node and the down phase are not the same. You can modify the theory and prove that everything I said before is the same, except for twice the term, you get the sum of the up and down. So it works. Synchronization goes to the point. You got to synchronize phase and frequency. This is a Chimera band, which, by the way, you meet very quickly. I'm just going to point out. It's a very reliable band. The SNR for the Chimera band, the variance, in other words, of the estimate, is 1 over the symbol SNR times the number of symbols I just pointed out. If you have 100 symbols to 100 symbols in training sequence. So as long as this is highly positive, you're done. The frequency is kind of a more complicated expression because it has this term over here, kind of the same here, but it has this term over here. So frequency is harder to estimate. Let me just put it this way. Even for a few hundred symbols. So what you do is, basically, if you're not happy with what you're getting, you can't get it down to 10 or 15 hertz, suppose you prove to be 50 hertz or something like that, that's not good enough. You then apply a super filter, frame by frame. In other words, you have a higher filter that smooths things over frames. So it's a progressive thing that eventually gets you what you want. You might not be able to get a perfect or adequate frequency estimate in one shot, but you filter over estimates. Let me just put it this way. And it works. It takes a little bit longer at the beginning to get, and it works. But yes, frequency is harder to estimate. It is the critical component. Timing. Let me address timing of symbols. When I beamform, I'm not interested in just in transmitting energy. I want to send symbols there, right? So because people are in different distances in clustering, their symbols will not arrive at the same time. So there's no point in getting the same phase if they're not also synchronized symbol-wise, right? And there's a whole other protocol for getting it. But the point is the following. Phase is the critical component because if you have a wavelength of, 1 nanosecond, you need to get down to tens of femtoseconds to get adequate frequency. It's very, very tight. Where symbols are, 10 megahertz, 20 megahertz bandwidth, so even 10% of that, it's not a big deal. So the timing of the symbol alignment is a way easier problem than phase alignment. That's what I'm going to point out. There's a lot of protocols. We're using some of the classical protocols of people synchronizing transmissions at the symbol level. Much easier. But you need to do it. You're not only sending energy, but you're aligning the same symbol at the same time. Dynamics, let me put it this way quickly. If the destination moves around like crazy, there's no problem. We put it on planes, we put it on drones. The destination dynamics don't matter, actually. Because as I pointed out, you really illuminate a patch. Okay, and within 10 milliseconds, how far can it go? You must go super Mach to move outside, so it doesn't. So destination dynamics, don't worry about it. Internodal dynamics, though, within the cluster is a different story. It doesn't take much of a movement, okay, relative movement of the nodes to actually switch, turn the phase off or be off phase. So there, we haven't really, we proved that you can walk, nodes can walk, and with walking speeds, you're okay. Because you stay coherent. But if you start driving around, that's a different story. If they're all collocated on a track and drive around, again, no problem because they're fixed with respect to each other. But if they're all in different platforms, we probably need, this is an interesting research problem, we need to do some Kalman filter or extended Kalman filter prediction. You estimate the dynamics and then you need to predict and pre-compensate the phase. I'm not going to deal with multipath.
There is a question.
Yes, please.
Regarding the synchronization, as you said before, whenever you transmit the symbols, they need to be synchronized. So the different radios in the actual transmission, they need to be synchronized. But I believe that the same will hold when it comes to probing, right? I mean, the same will hold. There needs to be some sort of time alignment whenever it comes to probing.
No, because the sequences you send are pseudo-noise sequences. So just need to correlate with it, the probing aspect is not really.
So what I'm trying to say is that if the channel changes very fast, and
yeah, well, right now we assume that the probe length is, let's say I need to compute it, it's very short, because you have 100 symbols at 50, let's see, 50 nanoseconds. It's, so let's see, 20 megahertz is 1 megahertz a microsecond, 20 megahertz, 50 nanoseconds, times 100 is, you're talking about 5 microseconds. In 5 microseconds, the channel doesn't change much. You understand what I'm saying?
yeah.
It's such a short time that channels change in the order of milliseconds, not microseconds.
Yeah.
Okay, so there's no dynamics for it. Is that clear?
Yeah, thank you.
Yeah. That's a good question, thank you. Multipath is a different story. I'll probably have to skip it in the interest of time. Because right now I assume line of sight. Let me just tell you quickly, there's multipath and people have looked at that. A multipath has a frequency profile, has nulls and blah, blah, blah. So what you really do to get the bottom of it, you beamform per subcarrier. You take frequency domain approach and each subcarrier is narrowband, this theory applies. You beamform per subcarrier or per group of subcarriers that have roughly the same phase. That's the practical solution. The problem there is, if you do that, it's like FTM, you have peak to average power ratio loss. You have to back off the amplifier. So you have to be careful if you gain or not gain. Because right now what we're doing is constant envelope transmission CPM. Because we just use one subcarrier and therefore we can maximize transmission. We can saturate the amplifier. So, but if there is multipath, significant multipath, and you can assume it away, you have to bite the bullet and do frequency domain beamforming. Let me just put it that way. Doable, just have to do it. Back to the question about throughputs. Right now, all radios send the same message, so it's a throughput of one message. Okay, we just get SNR gain by going further or whatever it is. We've extended the theory, pending patent, where the receiver now, the destination has an array. Let's say you have a destination somewhere with 4 antennas. Okay, now what you do is you have 4 clusters now. You multiplex the clusters. You have 4 clusters, and each cluster sends its own message. You can do it 2 ways, either incoherently or coherently. In other words, each cluster just blasts out its energy and you get the average energy on the other side. Or you do what the patent describes. Each cluster beamforms to a separate antenna. This is color-coded here. This color beamforms here, the green beamforms to the next one, the brown to the next one, and this one to the next one. If you do that, and that's one of the most surprising results, and nothing almost done, you get performance. This is outage capacity, this is bit array with a turbo code. You get performance like a SVD. So suppose you have a super genie, which doesn't exist, that collects all gains from all links and does the most optimal singular value decomposition, eigen loading of MIMO, that theory. And you say, hey, well, what's this upper bound? It's unachievable in practice. And this simple trick, the eigen loading and the beamforming, let's say, that's what I'm researching while I swim now. It's the most interesting result. And I want to understand it better, why that is. There must be something at work here. But if this is true, I'm basically walking into a distributed beamforming dancing. I can now actually increase some rate with this little trick of mine. Research challenges for those, and I'm done, for those, I'm time. For those interested, kinds of, as I told you, there's academic research, there's different algorithms. Nobody has done a thorough sit-down comparison for different scenarios, dynamics, nodes, and so on, to know where the delineating regions are, where you should really. There might be some cases where I can see working with a simple system, but not always. Our system is robust. Multipath, I mentioned that. It can be done. We haven't done it, but it can be done. Scaling. Well, what happens if I increase the number of nodes in a cluster, right? So, can I have 100 nodes and get 40 dBk? Can reach the moon. Obviously, because we have this ping-pong calibration process, you start hitting limits of what you can do locally, okay? But there are ways around it, you know. Or maybe you do hierarchies, you know, the clusters have subclusters with the cluster heads, and the cluster heads coordinate and stuff. That could be interesting solutions to increase the cluster size and get some spectacular gains down the road. How to handle local mobility, I pointed that out. It's an issue. We're thinking of using some advanced Kalman type of predictors for phase. In the case of multiple clusters talking to an array, there's an interesting combinatorial problem. Suppose you have 300 nodes, and the clusters should be 30 nodes each. So you can have 10 clusters. How do you assign them? Do you assign them randomly? Do you assign them by strength? Do you assign them by location? Do you assign, how exactly do you assign? It's an interesting protocol problem, just so. And we're also looking at merging remote networks. You have two remote networks that need to talk to each other, so you kind of use sub-deviant methods to connect them. That's it, basically. I view it as a toe in the door for a big area of distributed MIMO. There's been research, if somebody wants to read, there's a lot of stuff out there. There are practical challenges. The one thing you discover by working in industry is that papers can get you only so far. You start putting this together in the lab. I'm not doing it, others are doing it. Unfortunately, I'm not very versed in actual experimentation, but there's some fantastic engineers do that. And then you see how they use theory practice ping-ponging between the two to understand what's going on. I think this topic will be ubiquitous because you get drones, UAVs, flying base stations. As you know, people are putting base stations, cellular base stations around to cover areas. And so I can see that mushrooming down the road. Thank you kindly. Yeah, please.
I have a question. Yeah, it seems it works.
Okay, now it works.
Okay. I'm not sure if it works.
I can hear.
Yeah, okay. So
I had a question related to networks.
To which?
Based on your last point, you're saying, okay, there are going to be all this drone ecosystem, which could be a potentially killer use case. But, coming from industry, I'm always curious about that. Like, what do you see currently? It's going to be a very practical use case for some sort of distributed beamforming on MIMO. Because I think one of the reasons that it didn't fly in the way that people were expecting, because as you said, 10 years ago we had not only theoretical but also system papers as well that they're trying to explore the system aspects of such technology, is that the use cases or building something in practice is more challenging because these different radios, they need to be synchronized somehow, right? They need protocols and they need to talk to each other somehow. So I'm really curious, like, what do you see as a killer use case in the next, let's say, X years, or based on the current reality?
It's a very, very interesting and very insightful question. Let me just put it this way. First of all, you can split the wireless world into two camps, the 90% camp and the 10% camp. The 90% camp is cellular, or Wi-Fi, right? It's infrastructure based. And infrastructure vendors are trying hard to sell infrastructure. And therefore they're building small cells, femtocells, nodal cells. They're trying to basically convert each cell phone to a cordless phone if you really think it. They're going to be very close to you and serve you. But there's 10% of the cases today that cannot be accommodated, and those are all tactical military systems, cannot carry base stations around. Sensor networks cannot afford, especially for low power applications. Internet of Things kind of situations. Places where you just cannot have infrastructure, seas, oceans, skies, and so on. In other words, this 10% exists, and I think it's going to expand. Particularly if you start including aerial elements. Right now, people connect to Starlink and so on and so forth. But in the future, I think there will be a lot of activity of, let's just put it, roaming infrastructure on the sky. In general, in other words, we will see a continuous push for intense infrastructure, call it massive MIMO, whatever it is, that might be applied to downtown Manhattan and downtown Athens and downtown Hainan. And I expect that to continue. But there will be a lot of places outside the dense areas which cannot be served, and they have different needs. So I see that as an entry point to the second category. I don't expect the cellular infrastructure industry to stop expanding, but I can see a lot of ad hoc-ish applications arising, for which cellular is just not the answer. Agriculture, for instance, you want to put a base station in every olive tree, thing. It's not IoT. It's not the interesting angle here is I can use DBF to reduce power, because if you get a sensor here, another sensor here, and I need to reach a specific access point somewhere, I just pointed out that if they can locally share the message because of the n squared gain, because they want to reach this, they can reduce their power by 1 over n, not squared, 1 over n. So as n increases, you get a factor of n in power savings. You can extend life. It's a simple computation to see. So it's not just throughput, and it's just a range, could be power savings, significant power savings. So anything that does not fit the massive MIMO paradigm of cellular or Wi-Fi could be served by this.
So to be honest, what I had in mind is some sort, because it's extremely hot, is direct-to-cell communication, meaning that to have satellites serving mobile phones, right? This is a new hot thing right now. So I was kind of wondering to see how this will play on the infrastructure side, meaning that on the downlink, the satellites being the transmitters, because on the uplink I don't see how to play. But I was wondering how this will work, given the fact that you may have not very dense constellations and the satellite are moving extremely fast, and the link is extremely long as well. So a lot of challenges, even the, how's it called, this probe, if it travels such a long distance, this was my thought when I did this question. So this is what I had in mind, how this will play.
Yeah, well, let's understand a few things. Let's get our thoughts aligned on the following. Dynamics come into two flavors: Doppler spread and Doppler shift. Satellites have predictable trajectories. Okay, they're not random. You can compensate in advance their movement. So Doppler shifts and predictable trajectories are not the problem. The real problem I pointed out is not that, and also the large distances are latencies. They're not delays. They're fixed latencies. I know the distance, so I can compensate, for that. So whatever is predictable trajectory-wise and latency-wise can be pre-compensated without much of the real problem.
But just for this, the satellite has a huge beam, right? It covers tens or even hundreds of kilometers.
Yeah.
So my point is that the latency that you will see big on the center of this tile that they're covering can be significantly different comparing to an edge, right? So
yeah, but I'm not thinking of distributed beamforming from the satellites down, but from the users up.
So the problem with that is that how I can make my iPhone talk to the other iPhone, or how I can...
Okay, now you're pointing, very good. The real reason iPhones don't talk to each other, it has nothing to do with technology.
Yeah, of course. Of course.
It really is the effort of the 3GPP industry to control what technologies enter the game. There's no reason why they shouldn't be talking to each other, because each communication is encrypted. Now, if I hear your encrypted communication, if N nodes hear your encrypted communication, they can beamform. They can't decode it, they can't understand it, they can send it. There's nothing fundamentally stopping the cellular industry from adopting this and reaching the satellite. There is nothing technically. They don't want it, which I assume has to do with proprietary and system level aspects. And to be fair, there's another consideration, subtle consideration, which is the beam patterns I pointed out. They're concerned about interference. And in the distributed system, the arching pattern is not very controllable in different directions. So they want to make sure that you're not hitting an adjacent cell, okay? Could you control I have reasons to believe that there's simple ways to reduce those patterns, but the honest answer is it's not a technical problem. It's a policy problem. Will it change? I don't know.
So just one more question. I don't want to
No, I like it.
hijack the discussion, but let's say I go back and I call them in Apple and say, hey, look, I read this fantastic paper, let's do it on the iPhones, right? We're going to have our proprietary protocol, we don't care about other devices, because, you know, as soon as something is 3GPP is only when you talk to other vendors 3GPP compliant. Between iPhones, I can do whatever I want, right? So I will build my own proprietary protocol, and then we'll go from there. What throughput gains I could potentially claim, assuming not only the increase in SNR, right, but the fact that, for example, I need some messaging to be able, so I need to bear some time sources to be able to get my face aligned or whatnot. So it's like what throughput gains I could theoretically claim.
Other than as an argument?
Huh?
SNR related.
Yeah, definitely.
N squared. N is the number of clusters, size of cluster. Just right. You get an N squared gain.
N squared gain.
It's that simple. If you have 10 nodes, you get 100, you get 20 dB. Provably, no paper. You get an N squared gain. If I get
my point is that there's also a probe involved, right?
Pardon me?
There's a probe involved.
Yeah, minus the 10% that I just mentioned.
It's minus 10%.
Yeah. If there's 30 nodes, you get a 30 dB gain. I can close any link I want. It's not a technical problem. It's actually, the technical problem I pointed out at the beginning is the following. I cannot use my technique because uplink frequencies and downlink frequencies are not the same. F1, F2 are not the same in satellite systems. Most systems are FTD.
In cellular, there are plenty of TDD bands. So.
Yeah. In the TDD bands, let's get a project going and become all rich. If you can solve me the politics, I'll solve you the technology. We're talking to Qualcomm, by the way, because we're neighbors. But talking to Qualcomm, you understand how the big companies play the game. You know? It's a very political thing. That's all I'm telling you. There's technology and then there's politics. And all your questions are very important because they point out. What I'm arguing is the following. If cooperation is allowed to take place in the cellular world, there will be an explosion of technologies, gains, and so on. It will be just an explosion, but they don't allow it. So far.
Thank you.
This is all cooperation. You understand? It's a cooperative process, right?
Yeah, I mean, I have dealt with politics with Qualcomm a lot, so I know what you're doing.
I can hear you.
So I have been dealing with politics. I have been dealing with politics and with Qualcomm
A lot. So I know what you're talking about.
Yeah. But
So I know
it's
that's
interesting. I mean, you can start. The stuff we're doing is does not confront the cellular industry. We're doing it for tactical military radios. You know, there you can do anything you want. in the institutional world, and just put it this way, you can do a lot of things, so they can't dictate what you do. Okay. In fact, cellular things don't work in the middle. They tried 5G, it's also not in the target. They could use in, connecting high-level, tiers and so on, sure, by hardening it, but there's no way you can use commercial technologies and just can't.
Thank you.
Other questions?
That's an interesting, you raised some very interesting points, thank you. You can tell we've been thinking about commercializing all this.
But then the next project, you would say. It's done.
Okay, let's thank the speaker.